Consider the function whose information is given below. So we're told that f is continuous everywhere. We're told that the limit, now so there's a typo here. So you need to make this change. So the limit here is actually negative infinity, and this is also negative infinity. So there's a typo here. I'll have to go back and change it. So we're told it's continuous everywhere. We're given the end behavior. We're given a sign diagram for the function, the first derivative, and the second derivative. Okay? So let's remind ourselves what each of these sign diagrams is going to tell us about. A sign diagram for the original function, where the function's positive and the function's negative, this is telling us about the y values on the graph. If the y values are positive, it's above the x-axis. If it's negative, it's below the x-axis. All right? So this tells us where the function is above or below the x-axis. The first derivative, this tells us about increasing and decreasing. The second derivative tells us about concave up. Or concave down. All right? So it asks us to find the open intervals over which f is increasing. So looking here, increasing means I'm coming into the first derivative. I've got the first derivative positive. Think positive first derivative, positive slope. A slope with a positive, a line with a positive slope is increasing. And then at 3, it levels off. 0 slope, and then it's decreasing to 4, and then it's decreasing after 4. All right? And so we've got two open intervals here, 3 to 4, and 4 to infinity, and the question is, can I combine them? Oh, I'm sorry, we want increasing. I'm jumping the gun again. Sorry about that. Increasing, we just have the interval here, minus infinity to 3. That's increasing. Okay? Now for decreasing, we've got the two intervals listed here, 3 to 4 and 4 to infinity. And the question is, can we combine them? So we talked about this a couple days ago. So can we combine them? Well, here's the rule about combining. I need to make sure that in this case, see, the derivative here is undefined. All right? So I need to make sure that the original function is defined here. If it is, then I can just combine them. All right? So to combine these, I'd have to say is x equals 4, because that's where it's broken up here. Is at 4. Is x equal 4 in the domain? Okay? Well, I'm told that f is continuous on minus infinity to infinity, so 4 is in the domain. Also, I get that 4 is an x-intercept. So I've got two different places here that tells me, you know what, 4 is totally fine in the original function. So I can combine these to 3 to infinity. Right? So you see why we can combine those intervals into one big open interval? All right, now it's asking for concavity. So once again, increasing and decreasing, we want to look at the first derivative. For concavity, we want to look at the second derivative. And so here's the second derivative here. And when we think second derivative, we think locally quadratic. So we think about parabolas. So a negative second derivative, that's the sad parabola, so that's concave down. Positive second derivative, that's a happy parabola, it's concave up. And sad parabola, concave down. So it's concave down from negative infinity up to 4. and from 6 to infinity. And then it's concave up in between there from 4 to 6. Okay. Any questions on gleaning the open intervals of increase, decrease, concave up, concave down from the sign diagrams? If you've got the same sign on both sides, like in this case we've got negative and negative there at 4, to see if you can combine those intervals, you check to see if the point in the middle there is in the domain. Okay, then it says to determine the x-values of any where f has the following features. Well, let's see what's happening here at 3. At 3, the graph goes from increasing to decreasing. So at 3, that's going to give me a local what? Maximum. And in fact, that's going to be the absolute maximum as well, because the graph never turns around. So at x equals 3, I've got a local and absolute max. Do I have any inflection points? Inflection points, we're looking at the second derivative where the concavity changes. So it changes here at 4 from concave down to concave up, and at 6 from concave up to concave down. So I'd have 2 inflection points. Once again, I know that even though the second derivative is undefined here, I know that 4 is in the domain. All right. So to be an inflection point, you have to be in the domain. So local maximum, x equals 3. Local minimum, there was none. To have a local minimum, you'd have to have this happening. We didn't see any of that. 3 is also where the absolute max is going to be. Absolute minimum is going to be none, because if you look at the limit there, it was minus infinity. And the inflection point we had at 2 locations, was it 4 and 6? Let me double check that. Yep, 4 and 6. All right. Any questions on getting this information? Now we want to put everything together and sketch a possible graph. So I'm going to keep this handy, and we're going to look at the possible graph. Now, since we're not given the actual function itself, I have no idea the actual y value on the graph, except unless it's 0, positive, or negative. So here's what I do. Here's what I like to do with these types of problems. I'm going to draw myself the x-axis. Okay? And I'm going to put all the points on the x-axis that are important. So what do I mean by that? So I'm going to be looking at 0, 3, 4, and 6. So 0, 3, 4, and 6. And I'm going to start over here at the left as we're going off to minus infinity. So the limit as x goes to minus infinity of f of x, and once again this was a typo, so this is equal to minus infinity, that means that the graph is starting down here. Okay? And so what happens? coming up to 0. Coming up to 0, the function is negative, so it's below the x-axis. Coming up to 0, 0's in here. It's increasing. And 0's over here. It's concave down. All right. So if I look at concave down, there's two halves to concave down. There's the increasing half and the decreasing half. So it looks like this. It looks like this. And at 0 itself, the function is 0. So it's looking like this. Okay? The function's negative, so it's below the x-axis. It's coming into 0. The function is increasing and concave down. Now what's going on between 0 and 3? Well, between 0 and 3, 3 would be here. It's above the x-axis. So it crosses through at 0. And it's still increasing. And 3 is here. It's still concave down. So it still looks like this. Okay? So what's magical about 3? At 3 itself, it levels off and then starts to what? Decrease. So on my graph, it's going to come up to 3. And once again, I don't know what that y value is. So it's going to come up to 3. It's still increasing and concave down. And then it levels off at 3, and then it starts to decrease. And so between 3 and 4, let's check. Between 3 and 4, it's still above the axis. It starts to decrease, and it's still concave down. So then what happens at 4? Well, a lot happens at 4. At 4, the function reaches back to the x-axis, and it's going to transition to below the x-axis. So it's going to cross through at 4. But what happens with the derivative? It's decreasing and then decreasing, and the derivative is undefined there. Okay? So when the derivative is undefined, what does that mean? Well, I know that the function is continuous at x equals 4. So that gives me a couple possibilities. I can have a corner or a cusp. So it would have to, so a corner or a cusp looks like that. The problem with the corner and the cusp idea the problem with the corner of the cusp idea is these change from increasing to decreasing. This is decreasing all the way down. So what we must have there is a vertical tangent. So it comes in and just slices down like that. Does that make sense? It has to be decreasing on either side. So that's the only feature we have there to include. Now notice when you have a vertical tangent, the concavity is going to change because it has to get vertical and then on the other side. So notice that's also incorporated here. So it looks like vertical tangent is what's happening at 4. Oops. So we got to come in and we got to make it look like a vertical tangent. So all kinds of stuff is happening. We got an x-intercept there. It goes from negative or above the axis to below the axis. F of x goes from positive to negative. The derivative doesn't change. It's still negative, but the concavity changes. Okay. So now let's look at what's going on between 4 and 6. So between 4 and 6, this is concave up. But decreasing. And below the axis. All right. So concave up and decreasing. Well, here's concave up. And here's the decreasing part. Until we get over to 6. So what happens at 6? 6, the concavity changes back to concave down. So it's concave down and decreasing, so then it's going to look like that. So it comes over. Now the second derivative is 0 there, but the first derivative is negative. So it's coming in, it's still decreasing, but then it changes to concave down. So we have an inflection point here. We have an inflection point here. We've got a local and absolute max here. And that's it. I'll mark these down here. There we go. So it starts here, comes up through 0 up to 3. During this entire journey, the function is increasing in concave down. Then from 3 over to 4, it's decreasing in concave down until we hit to 4. At 4, it crosses through. The function goes from positive to negative. It crosses through the x-axis. Concavity goes from concave down to concave up. We're decreasing then, but below the x-axis over to 6. It's decreasing in concave up. At 6, it switches to decreasing in concave down.